This week, we're going to actually start looking into some static malware analysis techniques. So we kind of like glossed over a handful of them when we made that attack a couple of weeks ago. I'm going to start taking you into some tools that we use to do some of this stuff. So this week will probably be like the first real like static analysis week. Today, I'll actually just introduce some of the most rudimentary tools, and also kind of how I approach the data collection from them and how I approach the analysis of it. So, but I will begin with kind of some more conversation around the whole like file model and stuff like that. So, static analysis, how I kind of describe it is right here. The goal is to document the observations that you have about the identifying characteristics that a malware sample exhibits or contains. So if you were to be looking at all of the files on a disk, or if you were to be looking at all the sectors on a disk or something like that, the information that you glean from static analysis of a file is going to be information that would help you identify whether or not the malware sample that you were looking at is on that disk or is one of the files on there. So that's kind of the goal of it, is what a file looks like, what it contains, what its contents are. So I typically distinguish static analysis to focus on how it looks, so I'll usually describe it in terms of how it looks or what content it has, that type of thing. And it's different from dynamic analysis, where dynamic analysis is typically execution time analysis. It is what steps did or I should say what actions did the malware take when it was run on a system. So with static analysis, the information that you gather from it is usually very helpful in identifying any malware samples that are running on the system, but also any malware samples that might be dormant or inactive on there for some reason. A lot of times when you're getting targeted by cyber attacks, the attacks are not always successful, or at least not always 100% successful, but many times they still leave behind a trace of the attempt. So a good example might be if you have users that were, say, redirected to download like a driver installer that's really malware. Again, borrowing back from the example that we had earlier in the class. They try and run it, but then they stop, they stop the installation for some reason. That still sits in their temporary internet files folder for the most part on most Windows systems. So it sits in the browser downloads area. Wasn't run on the system, so you won't be able to pick up the execution time effects that it had. But if you were scanning the system for what it looks like instead of what it does, then you might actually be able to find it. And that's a really common hunting tool, is to look in the places on a system where a web browser would normally store files that it temporarily downloaded. So the downloads folder, or the temporary internet files folder on older versions of Windows, or the temp folder, or the Firefox maintains a large number of cache directories where it caches files for later use. So when we're analyzing files, and the exe files right here, that's a big one as far as backdoors and malicious tools are concerned. Generally speaking, when an attacker is trying to run programs on your system, generally they're trying to run Windows programs on a Windows system, and so the exe files end up being the one that we'll keep coming back to as a file format. But I have all these listed up here anyways, just to kind of reinforce the container logic that I spoke to earlier. In fact, the PNG file specification refers to PNG files as being data streams. So you're using the stream terminology instead of the file terminology that we had before. And how they describe it according to their documentation, which I do have linked right here. So their standard is that they're data streams that begin with a sequence of 8 bytes, so a very specific sequence of 8 bytes, and then it's followed by one or more chunks. And the chunks themselves have a substructure. So each chunk has, for instance, a field that defines what type of data or what type of chunk it is, and there are multiple defined types of chunks within the PNG file specification. So I'm not going to dive into all of them here for the interest of brevity and class time, but the chunk types that are accepted by the standard, at least, are all defined here. So if you ever want to look into it further, the link is here. Furthermore, exe files are generally the files interpreted by Windows to contain like program or dynamically linkable library code. So that's your Windows EXEs or your Windows DLLs. Another common name for these is the portable executable, or the PE file format. And that's generally speaking when you're talking about what Visual Studio and a lot of tools are going to call these, or when you're trying to search for information about dealing with their data structures. Rather than searching for exe files, you'll generally search for this term right here, PE32, which would be the file format you'd be looking at. So I can, the best, I should say, document for describing its structure is here, so I also put this in the slides. So I did not find a very good reference online for it. I will have all this stuff posted as well later on tonight. Another file format, so I grabbed 3 because these are common file formats. Another common one is typically, the formal name is the MSCFB, or the, I forget exactly what it stands for. I think it's like complex file something or other. But for lack of a better term, this is the file format that your doc files from Microsoft, from older versions of Microsoft Word, your Excel files from older versions of Microsoft Excel, the XLS files, and the PowerPoint. So all the old Microsoft Office files, they actually share this file format. A lot of other files that Microsoft distributes as well share it. The one that you might be extremely familiar with is the MSI file that's used as a Microsoft installer. It's not really an exe file per se, but it's more of a one of these MSCFB files that has specific type definition to it to be a Microsoft installer. So also, Microsoft has published their official documentation about how that file format is constructed, and it's here. So I always feel like these 3, plus the PDF stuff that we looked at earlier on in the class, so I should say those 4 file formats give a really nice variance of how file structures are typically designed, and also just really good reference examples of how files themselves have structure. And kind of one of the reasons I'm getting into this is that the structure then goes and defines what the meaning of the content is, so it gives context to the content that's stored in certain places of these files. And so we'll jump into the PNG file for a moment to kind of give you an idea of what it looks like. So basically how the PNG file looks is, here's those 8 bytes that I said. So it starts off with 8 bytes. And then after those 8 bytes, it actually has a sequence of records. And so this particular one was specifically pulled from this stegosploit.info site. And it's intended to show you that there's a bunch of different data types that can go into a PNG image file. So generally you see a PNG image as just being, pixels, and you know that probably from your use of them that they're typically a compressed file format. So generally speaking, this data here, this pixel data here, is some sort of compressed data that then gets interpreted by your browser or other image software to show, a rectangle of pixels. The other thing that's neat is that it has all these other type fields, or I should say it has all these other data types for chunks. So this header file, or this header chunk type here, and I'll kind of dive in here, each one of these things, so there's 1, 2, 3, 4, 5, 6, so each one of those 6 things is a chunk. So there's 6 chunks in here plus the final chunk, so I guess there's technically 7 chunks in here. The specification says that it starts with these 8 bytes, and then it always has a chunk that is this IHDR, or iHeader, or image header chunk. And then it has it has 0 or more data chunks internally, and then the last one always ends with this iEnd chunk, or image end chunk. So the specification says that nothing is found past that chunk. And so if you look at this, it's literally just a list of all these chunks. The chunks individually themselves can have variable width to them, and you can repeat them as well. For instance, there's 2 text chunks here. And then I suppose that the goal here would be that if you're extracting this information, you can kind of stitch the text together, and you can embed comments or something like that into the image if you like. There's also other chunk types as well that are supported in there, so there's by no means an exhaustive list. The exhaustive listing of what's allowed is up here, and then there's probably some modifications in certain libraries that allow for other chunk types that aren't part of the standard, depending on what somebody's uploaded to GitHub and what you use. But kind of what I'm getting at is like, the way this is set up is that in each one of these chunks, there's a set of bytes that each chunk begins with that's really, I guess, 2 bytes that defines the length. So there's 2 bytes that define what the length of the chunk is going to be, which means that when you extract all the chunks, the first 2 bytes, whatever the content of them might be, are always reflecting the length. So you can, if you know that structure ahead of time, that means that you can grab those first 2 bytes out of there, and you can compute a length value out of that. So you can derive a length value out of that. If those same 2 bytes, for instance, are sitting in this field, even if the data is the same, the meaning of it is different because it's sitting in a different context, it's sitting in a different field. And so that's kind of what I mean by structure. So the PE32 file format, the exe files that were frequently used to dealing with as programs and everything like that, they're a bit more complicated, but they actually work off of some of the same principles that I just showed you that are used in the PNG file format. Of course, this file format is much older than the PNG file format, but how this one's set up is all of them, in order to be a legitimate PE32 file, they actually always start with a certain amount of data that's the MS-DOS MZ header, which is really just a short number of bytes that includes the values M followed by Z. And we saw that when we were analyzing the program file, the backdoor that we extracted from the PDF earlier. And then they're followed by the DOS stub, which is just a little tiny DOS program that's embedded in the top of it. And the reason for that is very legacy, and it's because Microsoft Windows was built by a company that originally built Microsoft DOS. And when they moved to having 32-bit executables, or I should say, or even 16-bit executables that Windows could interpret, they wanted it so that it was very user-friendly. So they made this convention where all those programs, if you try and run them from the DOS command line, you've probably seen this before, it emits a little string that says this program must be run in Microsoft Windows. So they did that from a usability perspective, and for whatever reason, they have kept that in their file specification forever. So I merely point this out because in some cases, there may not be a very specific technological reason why some of the file formats are structured the way that they are. There's all sorts of historical reasons and reasons that don't lend themselves to any sort of like efficiency or optimizations or anything like that. Say, in some cases, you'll find that the way file format is structured does not necessarily have to be driven by any sort of, extremely well-sound logic, I guess, for lack of a better term. And I always felt this is a really good example of that, because you can see that, I think the last version of MS-DOS that was really commonly used was probably in the mid to early 90s. And we still have a remnant of it living around today. Or I should say we still have compatibility with it, or backward compatibility with it, baked into even the 64-bit executables that you'll run on your 64-bit Windows today. But getting back to this, after those things, then you end up having the PE file header. So you actually end up having a header that has all of the fields and information that's needed for the 32 or 64-bit Windows to set up memory for it and load it in the operating system. You actually have those things crammed after all of that MS-DOS compatibility stuff. Then you have another header that, for whatever reason, is called image optional header, but almost always shows up in executables today. It's probably another piece of information that has some sort of legacy meaning from a long time ago that then stopped being optional more recently. After that, you have a section table. And this is really for an exe file, this is really a table of contents. So this is a table of contents telling your operating system where all of the blocks within the file are. So, and then finally after that, you actually have what they call the sections of the file. So in Windows, a program that you've compiled is generally carved up into what they call multiple sections. And a lot of this was done because of the way that they manage data in Windows. If you've ever used Visual Studio for doing like visual application development and stuff like that, you'll know that you have, a lot of times you have like the dialogue and the UI editors and stuff like that. And you also have a string table that you'll have built in there. And sometimes you'll have like internationalized strings and stuff like that baked into it. And then on top of that, you have the source code files that you're actually writing your C++ or your C# code or any of that stuff into. So what Visual Studio does is they actually compile all these different things into individual sections. So all your source code files typically get compiled into machine code. And then they get embedded within this section that's called .text right there. A lot of the static data that you've made, that you've embedded within your program, typically ends up getting stored within the data section here. And then a lot of the, if you've used a dialogue editor to make UI for whatever application you have, or you've used the string tables, or you've decided to add icons to your program and things like that, a lot of that information is typically stored in the resource section. And each one of these sections themselves are almost a file unto themselves. So they have their own defined structure. So the resource, I just named multiple things. You can have a string table in there, you can have a dialogue in there, you can have an icon in there. Each one of those things are little tiny files that all would be subcomponents that are each embedded within this resource. So it stands to reason that the resource section of the file also has another directory, just like this section table up here, describing the objects that you've stored within it that's particular to the layout of the resource section. Likewise, the data has the same, so it's going to have information that connects the data that you have statically compiled in your program to the variables that reference that data, or that data is used, that are used within your program to access that data. And there's a whole bunch of other sections as well. And one thing that makes it even more interesting or confusing possibly is that the names that you see right here are actually just very common conventions that Visual Studio uses. But they're actually not required to be named these things. Sometimes, and a really good example would be the Borland Delphi compiler, which compiles Delphi or Pascal code into machine code. We'll actually use different names for all these things. So instead of text, sometimes you'll see code instead. And in order to make sense of this, what Windows has embedded within it is they actually have type numbers. So in addition to the name of these sections, up here in the section table, there's also going to be type fields associated with them as well. So I'm going to jump out here and kind of show you one tool that I use for dealing with these things. So there we go. So I've actually gathered together a few random files that I found to be useful. So let me see if I can see this. Whoops. Yeah. There's a tool for Linux that's called objdump, and I think actually, yeah. If you have installed, I will actually have a lot of this stuff. So I'm right now using the Remnix VM that I'm going to give to you guys, which is basically Remnix, but then also has a few other tools in it that I've added to it that I find useful that don't come in the base image. And so this is one of them, which is a whole bunch of the Windows 32-bit and Windows 64-bit development tools. So there's an entire set of compilers that you can install on any Linux system that allow you to build programs that are targeted for Windows. So you can build your Windows executables and stuff like that. I've seen it used by some adversaries in the past for building malware, but I also find it's very useful for doing analysis of those files. There's a number of Windows programs as well that can do it. But one of the things I found that's very useful with the Linux-based tools is a lot of them work off the command line. So if you want to process the data that it's finding and store it somewhere, or work on it, or parse it, or something like that, it lends itself to being able to do that. So, whoops, I missed a flag here. So generally, what I try and do is this one is using this objdump tool. So if you've installed any tool chains in Linux before for doing software development, a lot of times if you just run this tool from the command line, it will search to find out which version of the tool works for the file you're trying to give it. So in this case, this is going to identify that my file is a Windows program, and then it's going to try and use this version of the tool. So it's basically going to intelligently figure it out and run this thing that I have up here. But I'm going to just do it like this. And so what you can see is that it identified that it's a 32-bit PE file. It's targeted for, it says i386, which is basically 32-bit architecture. You can see that in the PE header, it managed to extract a whole bunch of information that was embedded in there that tells it, for instance, the size of the code, size of uninitialized data, so the address of entry point, so when you load the program in Windows, where the first executable instruction is considered to be within this file, where to load it, all these things. There's all these numbers and values that are embedded within the file in order for the file to tell Windows how Windows should structure memory in order to start executing the code within there. It tells what versions of Windows it's supposed to be targeted for, or at least what the minimum version of Windows it's supposed to be compatible with is. And then we can go down here and we can see they have the data directory, which you saw earlier. and it actually tells where a whole bunch of other informational tables exist. So for instance, I mentioned that there's all the different resources and everything. So there's a resource directory that tells you where the separate components within the resource section are. So it's telling you where to find that. Or I should say it's telling Windows where to find that, but also you can find it too. Another thing that's common in Windows and requires data structures within the file is Windows has a lot of dynamic link libraries, these DLLs. And the reason they have this is because there's a large number of system functions that exist. There's a lot of system API calls that exist in Windows, which need to behave differently depending on which version of Windows that you're using. So for instance, if you want to run an application under Windows 8, then the file open close calls are going to behave differently than the file open close calls that came with Windows XP, because Windows 8 has a whole bunch of different features that deal with like file system code, file access, permissions, stuff like that. So because of that, instead of hard coding into any program a specific way of opening and closing files, or doing a whole bunch of other things that you can do in Windows, they load, or I should say they use function names that are listed in these DLLs, and they just embed references to those. So they give the DLL name, and then they give the function name. So when Windows loads this up, Windows 8 loads it up, it doesn't care really what version of Windows this particular program was supposed to work with. This program tells Windows 8 that it's going to use some code that is stored in kernel32.dll, and it wants to use these functions here. So there's a whole bunch of other functions inside of kernel32.dll, but these are the ones that this program is going to use. So when we're doing analysis of executables, this is another big piece of information here, because some of these are, you can look up information about what the function is supposed to do on Microsoft's like MSDN website, but also a lot of them just intuitively I can look at. So for instance, a really big one is this one, that is debugger present function call. So this is not common on all exe files. For instance, let me see if I can. Yeah, so here's the installer. I don't know if this will work or not. Oh yeah, there we go. Yeah. Well, it doesn't have it there, but I was trying to see if I could find. Let's see. So there's like this Notepad.exe here, so maybe that one will be a good one to compare to. Or maybe not, because it doesn't look like. No. Okay. Well, I can try and show you what I was going to look at there in a second. But basically, I can tell you that using the information that's here, I can get some idea of what functions of the operating system this particular program is going to want to use. And therefore, I might be able to glean some insight into the capabilities that this program has. So a good example is this is debugger present. So whatever this program is, and I know it's malware because I pulled it off of a malware site, it wants to basically ask Windows if a debugger is running or if a debugger is installed. So why a program would do that is possibly because it wants to alter its behavior in that case. For instance, a common approach with malware might be testing to see if this is here, and then trying to prevent you from trying to reverse engineer the program with a debugger by immediately exiting if it finds out that a debugger is present. So that would be an example of, say, behavior that it's trying to do differently. Another thing is, I think there's create directory. So in addition to creating files and deleting files, which might be really common operations for any sort of program, creating a directory may not necessarily be all as common. Depends on the program, depends on what your expectation is. Also, from a malware perspective, that'll give you some insight into if you already know something is malware, then recognizing that it wants to use, say, the create directory function, create file function, stuff like that, can indicate to you that it has capability to allow somebody to install files, create new directories, write stuff to disk, maybe bring in more malware. Another function that also does that is create process, which is what any program that wants to execute other programs typically brings in. So you can use a tool like this to walk through what operating system functionality is trying to be accessed by this particular malware sample. And all this information is embedded within, in this case, inside of one of the sections. So it says right here that there's a .rdata section, so another one of those sections that it showed you on that slide that has the name rdata. And it has, or I should say, this program has a parser that can read the contents of that rdata section and can actually turn it into a data structure for you to review. So another thing that it does, which you can identify from it, is this ADV API 32.dll. So it wants to use that as well. And then it looks like it's attempting to pull in a bunch of cryptography functions from there for some reason. So that could be informative as well. That might indicate that it likes to read and write encrypted files to disk. Like maybe, it's going to have some other data on disk, like a configuration or something like that that's encrypted, or it's going to download one from the internet that's encrypted or something. That can give you some insight as to whether it's trying to make use of encryption. So another thing that it does, so shell 32, there's a shell execute function which allows it to run commands. Is very similar to the system function in Linux if you've ever used it. And there's used as the LZ32 DLL. So you can see here that it has imports to try and interact with that to deal with compression. So if you go and look this stuff up on the internet, it'll tell you it's dealing with the LZ compression API. So, and then here's the functions from the Microsoft Visual C runtime. So these are the common functions that that you might see in your normal POSIX API or something like that, standard C. So, and then finally, here's the section listing. So in this case, this particular file, so this exe file has 4 sections, each of which has an index. So it gives an index to each one of them, gives a name to each one of them, and then gives a size. So each one of them, they all have different sizes. So you can see the text one, which is where the executable content is stored, is one of the larger sections. And then this rdata and this data section are smaller. And then this resource section is extremely large, likely because it probably has like a icon embedded in it or something like that, which is going to be an image file, which is going to be big. You can also look at one of the other ones that I have here, like this one. And we can see if this one, so you can notice that kernel32.dll on this one is a much smaller list of imports, what we call function imports. So for instance, this one isn't using that is debugger present function. It's also not using the create directory function or anything like that. In fact, it looks like it just uses the move file, and that is possibly it. Also has the win exec function, and has a handful of other things. Doesn't appear to interact with the crypto functions for the ADV API. It actually uses some other functions instead. So these, if you look them up, these deal with the Windows registry, which all of these are operations that allow it to make modifications inside the Windows registry, which is where a lot of the system configuration lives in Windows. So in Windows, when you go to Control Panel and change any of the settings in Control Panel, or you install new drivers that need to run on boot and things like that, all the information that's under the hood that governs where all those checkboxes are checked and where all the text is entered in there, that's all stored in the Windows registry. So this backdoor looks like it actually interacts with that in some way. And you can gather that it has the ability to actually make modifications to it. So not just read the data in there, but actually write new data into it. So this thing might be trying to mess with a user's configuration, that type of thing. So again, these are this is information that you can glean just by using the structured data parser that we're doing right now. So I'm going to jump back to the slides. So some of you who are familiar with, say, automata or compiler theory might be familiar with this notation here. It's commonly used in a lot of documentation on the internet for, say, format specification and things like that. It's also very common for you to write it out if you're trying to build a parser for a particular file format. So I've done a highly simplified version of that PE file that you saw earlier, just based on it. But basically, this is a what they call Backus-Naur form, or BNF, which is, I'm going to use BNF so that I don't like butcher the name constantly. It's just a standard way of defining the format of a structured file or format of a structured stream. So it's really common with like programming languages and stuff like that. And those of you who have taken or will take the compiler class will run into this. But it's also very common. You'll see it used a lot in some of the man pages in Linux and stuff like that, and some of the documentation. So later on, I'll probably bring it back up when we're starting to analyze the contents of certain malware files, especially the data structures within them. So another approach that can also be extremely helpful to you could be to define them as C data structures. So this is me going into the actual specification and finding out what the field width is for each one of these fields, and then embedding it right here so that you can use it. Basically, these two are more or less equivalent. The latter one allows you to define what the structure is going to look like so that you can have a compatible structure to deal with your source code and everything. So if you want to write a tool or something like that that analyzes PE files, this would be a good place to start with a data structure defining that. So this was, I was talking about that. So I walked you through some stuff that's like well-defined file layouts or data structures, because that's basically what they are, is they're just structured streams. You're probably going to run into data that's structured like that very frequently, but also you're going to run into a lot of unstructured data. You're going to run into a lot of data where you can see the content there, but you have no idea, say what it means. So structured data, I mentioned this earlier, but here's a more delineated definition here, is content that has meaning or context associated with it based upon its organization. The information that you're getting is really a combination of the data bytes or the contents, so the values of the bytes, as well as the placement of the data within a particular structure. So the value 1000 has a different meaning when it's in the field for section size versus the field for PE header offset. So it has a completely different meaning to you in both of those cases, but it's also the same value, which is 1000. And I'm being very pedantic about it, but it really is that simple, but it makes a huge difference later on when you're talking about trying to describe how you're going to explain the findings and that type of stuff. So in structured data, what I typically call unstructured data is content, but you don't really have any assigned meaning or context associated with its positioning. So you may find the number 1000. You may find it 1000 times within a file. But unless you know the layout of that file, you just know that the number 1000 happens in that file a bunch of times. That definitely is a important thing to note, important thing to document, but you don't know what it means. So the task of reverse engineering, which is going to be one of the skills that we're going to be teaching with the class, includes attempting to derive what this meaning is based upon your findings in malware analysis. So you're trying to work backward. You have the content, but you don't know what the structure is, because that's the adversary's secret sauce, basically, is the structure. They have the source code. They built the tool. They didn't build it to any standard in some respects. And so it's your job to try and work back to find out, or I should say, to fill in the context gaps as much as possible for the unstructured data that you find yourself with. So data extraction ends up being an extremely important part of the process. So I showed you one structured data extraction tool just now, which was designed to extract a whole bunch of the program data from EXE files. And that's extremely important because it's going to be the most common file format that you'll deal with when doing malware analysis. But another tool that exists is actually part of this open source Perl project called exiftool. And I think it actually has a much, I'm going to copy the link address here. It has a much longer name to it that's a more Perl-like name. But we always just typically refer to it as exiftool. So this install.exe is what I was looking at. I actually have this program, and if you recall, I tried running this program in my Kali VM about a week or two ago, and it epic failed on me in class. But I actually tested it on Remnix, so I have it installed in Remnix, and it seems to be working really well. What I wanted to show you back then was this, is that it goes into the file, and in this case, instead of doing what objdump did, which was to extract a whole bunch of the EXE specific data, this one attempts to extract some other structured data in there, some of which is EXE specific, but also some of which is more general. So for instance, some of you might be familiar with the, let me go, actually I'll load up my Windows VM and I can show you. You might be more familiar with some of this information as it gets represented here. So, come on. Oh, there we go. So if I go here to properties, you might be familiar with this screen, which allows you to see a whole bunch of information embedded within it, like the description, the copyright, file version, internal name, that. So anyone who's used Visual Studio to build an application in Windows might recognize some of these fields as ones that are available for you to fill in the application wizard or in the version info thing. So this program exiftool has a parser that can actually extract that information plus some of the other stuff. So you might remember these things as being these were fields that objdump actually saw. So some of those fields from that tool are actually used in here, as well as like the machine types, so architecture and stuff like that. It also tells you when this file was compiled. So in this particular case, we're looking at a program that I got off the internet at some point in the past couple of years, but it was actually compiled way back in 2011. So there's all these little pieces of information here that are in the structured data that you can extract. And so this is one tool that I've found is very useful for doing that. I'm going to jump to the website that I pulled from the tool and kind of show you. So exiftool has support for a whole bunch of file formats. So it lists them all here, all the way up to, and it was primarily designed to support extracting image metadata that was stored there by cameras. So like when you're, like for instance, when you take a picture with your phone, like, you know, I've got mine right here. In many cases, it may store like the GPS coordinates. It would store the type of phone. It could even store like the lighting information at the time and all sorts of other information. The people who made this tool thought that exact same concept would be useful on a kind of more broader application. So on any files that have metadata in them. So I'm going to try. Yeah, here's a supported file type. So this is an entire listing right here of all the different files that it supports. And you can even go in here to each one of them. So like this is the LNK file or the Microsoft shortcut format. So when you are in Windows and you say create shortcut to a file, this is the file format that's created. So it goes and discusses it here in, you know, in detail. Likewise, this is an open source project. So I'm pretty sure that somewhere around here I should be able to get the source code for it. And I'll just do this. Okay, so here's the SourceForge project page for it. And so we can go here to code, and then I can go in here and maybe look at, I don't know. Here we go. So this file, oh, whoops, that's what I wanted to do. I can go to the module that was modified. Here we go. So like this JA MWG. So I can go to this file here, which is like a specific type of file, and it has a whole API that you can see. So if you know Perl, I wish this thing would go away. So if you know Perl, you can go through here and you can look at it. But it tells like the different groups that it's got information in, the different keywords that it can pull stuff for, and then like further down here, it'll actually have code that describes how it goes to fetch this information from within a file. Yeah, so recover strings which are truncated by IPTC data set length limit. So here's the code that's being used to try and pull that information out. So it's got this whole API for building these little tiny file parsers. This is a really common thing for people to make a parser and then dump it into this, this file format. Or I should say dump it into this program, and then everyone can use this program for just arbitrary file metadata grabbing. So I will go over here. And so we looked at that exe file, but I also have a PDF file that we can look at. And I can use the exact same tools. I don't need a bunch of different tools. I don't need a bunch of different tools in order to look at different types of files. So I don't need a PDF version of a tool, and I don't need an EXE version of a tool, and I don't need a doc version of a tool. And you can see that using module for PDF that's built into it, which it probably has like a pdf.pm or whatever, it goes through here and it gets some of the information that's common across a bunch of different file formats. But then down here it starts to differentiate. It's PDF version, so it can actually extract the version of PDF language that it's using. if it's using any sort of encryption, what kind of encryption it's using, what the PDF modification date was. So let me see. Yeah. So this is the modification date embedded in the PDF, the last time it was edited, and saved into the file by a PDF authoring tool, which is different than the actual file system timestamp. And then there's also a creation date, so you can see that this PDF was, at least as far as the file is concerned, has an initial authorship date of 2008. And then also the last time the metadata was changed within the file, which is the last time the file was modified. Has a title for it. So this one says like the title's right here. Who the creator was, so in this case, whoever this is. The description is animated 3D PDF. So you can enter when you're using any tool that allows you to create PDF files. Like if you've used your Mac and you've saved as PDF, a lot of times you can actually edit these fields when you go to print as PDF. So, so the idea here is just to kind of get you all thinking about kind of design patterns when you're working with tools, when you're working with analysis, and that what they've found here that's very easy is having one tool that has this like modular framework where you can load like 1,000 different modules into it. So it's got like 1,000 different file format modules built into it that all adhere to a common API. And then when it's running through, say, a directory of files, it just basically runs all those files up against the modules, and the modules tell the parent application, which in this case is exiftool. They tell exiftool whether or not they're actually designed to handle that type of file. I was actually going to also go up here and see if, yeah. So here in SourceForge, so lib image exiftool is like a folder that's inside of that project. You can actually see all of the different modules that are each one of the unique parsers for each one of the different file formats. So PDF is right here, and I can actually jump into that one. It'll load up. And it's got a whole bunch of defined data structures and file types, or not file types, data types and things like that. And then it has like locate any object. So it has all of this helper code that's designed to assist the module that's using a certain API that's defined by exiftool to basically walk the document structure and extract out all the pieces of information that help populate what I showed you right here. So I'll make sure that I share that info, like a link to the PDF module, or the Perl modules and everything too. So kind of like also another sidebar is that you've seen I've been using Python for a lot of stuff, but there's also Perl will come into play, and C will come into play, and C++ will come into play as well. So all these different languages end up coming into play. It's very useful that if you haven't done it already to try and become familiar with like Perl, Python, PHP, C++, C, C#, Java, and a whole bunch of the other languages that are out there, because very likely, at least in that scope, we're going to be analyzing files that are written in those different languages. So I'm going to jump back to the slides, talk more about data extraction. So what I showed you there is basically a bunch of different approaches to doing structured data extraction. So another thing that's common is unstructured data extraction, and that's where you, and I'm just going to jump, okay. That's where you are pulling the content out of an artifact, out of a file, out of a data stream. A lot of times you're trying to look for content that maybe matches a particular pattern or matches a particular form, has certain content characteristics to you. or that you're asking for, and report those findings to an analyst. But it's going to be up to the analyst to derive any sort of like meaning from them, or even determine if they have enough information to derive meaning. So an exceedingly common utility that I put right here is the strings tool that's distributed with nearly all Linux systems. So an example is if I want to show all the strings from a particular file that are greater than or equal to length 6, I would run the program like this. And those of you who are familiar with grep and regular expressions, I just decided to kind of give you a long form explanation of what's going on behind the scenes there. But the idea with strings is you start at the beginning of a file, and then you walk from the first byte in the file just forward until you hit something that is a human readable character. So if you're all familiar with the ASCII table, actually I can probably bring that up here. So ASCII is the encoding that is generally the 8-bit encoding that that maps numbers to certain characters. And so this is the ASCII. This is an ASCII table right here. Do this so you can see it. What you'll notice, and you may already be familiar with this, if you are, just bear with me. The first 32 characters of the character set are, generally speaking, what are called control characters or non-printable characters. And then, after that, you have the first printable character is the space character. And then that's followed by all of your alphabets and punctuation and numerals and stuff like that, all the way up to this character, which is another delete character, or it's whatever the operating system wants to interpret it as. So what I'm doing is I'm going through and I'm looking for sequences of characters, so contiguous sequences of characters that are either 6 or longer that fall within this range. That's what strings is doing. I'm going to put this back at a normal zoom level. And the reason it's doing that is because that ends up being data that is most easily interpreted by your brain, interpreted by your eyes and your brain and everything. So it's easy data to work with. As you also noticed when we were going through with objdump and those tools, there's a lot of human readable string references because the source code has to be written by humans. So the artifacts left behind by that, like the function names and the DLL names that the functions are supposed to be being requested from, the string data that you put in between quotes to make user messages or file names or things like that. All of those things end up using human readable characters in order to make them work. So there's a lot of information that you can gather from a file by eliminating all the bytes from your view that are not human readable and then sticking with the ones that are. So for instance, I can run that program on this file, and then I can see, if you recall, I mentioned earlier that all Windows programs began with a MS-DOS stub, which is a little tiny 16-bit DOS program that if you ran it on an old version of DOS, all it would do is say, this program cannot be run in DOS mode, or this program must be run under Microsoft Windows, or something like that. So you aren't seeing any of the instructions that make that occur, but you are seeing that message being embedded within the file because it has to be statically embedded within the file somewhere. Sometimes you are seeing some overlap for other data that is, say, instruction data that just happens to collide with the visible characters. But then you'll see something like this, which is, looks like all the alphabets from A to Z, then the lower cases, then the numbers, then the plus, then the slash. So I can tell you that I'm looking at this, and this is a lookup table for the alphabet used for encoding or decoding base64 data. So when you are using an algorithm like that to encode binary data into another format, you need to do a data translation. Usually, if you've written any code like that, you usually fill an array with what your lookup table is to map numbers to bytes. And that's what they're doing here, is you're seeing the human readable component of that lookup table of theirs. And then you can see all those function names that we saw were in the import list when we ran objdump. So they're also in human readable form here. You can see other things in here as well. There's all those MSVCRTs, so these are even stored in the same order that they were when objdump extracted them. You can also see these, which suggest that this program has some sort of code built into it that wants to use the WinINet or the Internet Explorer DLL to make HTTP requests back and forth. Also, there's some more data in here that actually looks like what I'd call C++ format strings, and you can tell those things if you've ever programmed in C++ before or C and you've used the printf function. If you have strings that typically have like this %d in them or a %s, like this one down here, or %x, or any of these things, generally speaking, those are format strings that are supposed to allow you to print a informational message to a human that then is supposed to have binary data converted into a human readable format. So like this %d is going to convert binary integer data into an ASCII number using the normal characters 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So this, looking at this, I can gather just from looking at this that it seems to be trying to tell somebody information about the physical drives or the hard drives that are in there. So, that might be helpful. So this right here looks like a report that's very nicely lined up. So you can see that it's designed to be printing information in a way that's organized to be easier for a human to read. They're using a lot of spacing to try and make sure that everything lines up in columns and stuff like that. So typically, if you're trying to write code that works, that's supposed to report this to a program, then you wouldn't have the data organized in a way that's very easily readable. But if this is supposed to be, if this is intended to be interacted with by another person, then you do have that. So if I already know, as I do, that this is a piece of malware, then for some reason this malware has embedded within it the ability to communicate back and forth using the HTTP protocol, and then also to tell somebody who's not the person who owns the computer, so tell an intruder, detailed information about the devices that are plugged in and stuff like that. So like the USB drives, the hard drives, and all that information. So it might be useful for an attacker who wants to maybe keep track of who else is using a system that they've compromised. Like if they've compromised a workstation sitting in a library that has a lot of human traffic coming back and forth to it. This can help them keep track of people, or this may not be something relatable in, say, our environment here in the US, but in a lot of other countries, the internet cafes are still very popular, and shared workstations at those places are still very common. So somebody compromising an internet cafe with a backdoor like this, when they have access to that machine and then leaving, and then they can go and monitor anyone else who comes into that internet cafe if they want to. And so you might see techniques like this, so they can try and keep track of who's coming to that cafe and plugging in their devices. Because if you don't use a username and password to log in that identifies you, a lot of times using the same USB stick over and over again can tie you to a particular session on a system that's compromised. And so that might be, I'm just kind of hypothesizing here as to what might be the value for an intruder in collecting this information and having a report of it. So, let's see. Yeah, and so that's the big thing with say data extraction, is you're trying to pull all these pieces of data out of there and then document it. You document it, draw conclusions from it, that type of thing. And also, I'll just go, and sorry, keep jumping around here. But the other thing that's useful here is that when I'm going through here, it's very likely that the adversary wrote this exactly as it's written because they thought that it would be very helpful. It was a very good representation, a very good presentation for them. A lot of times that can indicate that, or I should say, that's a very unique information or a very unique sequence of bytes to this particular file. So it's very likely, or I can conclude with like pretty high confidence, that I'm not going to find another program that shares like all of these strings with that exact formatting. So me extracting this information is very uniquely identifiable information for this particular file. And we can contrast that with this, which this particular function, if I was to look for it on the internet, it's actually a function that this thing's referencing from this DLL. So when you run this program, it loads this DLL, which ships with Windows, and that DLL provides all of these functions. So there's a lot of programs out there that actually use these. In fact, anybody who wants a very easy way to download stuff that's hosted by HTTP or wants to be able to communicate using HTTP, say like post telemetry data or something like that, may use these functions. So I'm going to find a whole lot of programs on the internet and programs at my company that are on hard drives at people's computers that have these particular functions embedded within them. But I am not going to find probably any, except for other copies of this backdoor, that have these specific strings in it that are formatted exactly like this. That's not to say that the adversaries can't go and in the future change some of these strings around, but generally speaking, anything up to this point, if I was to analyze that and then go look for those strings throughout my network, then say if I had found that one machine was misbehaving, I might find the other 10 that are behaving normally but are still infected with whatever this is. And that's the sequence of, that's the sequence of steps that is most common in a lot of incident response environments where the malware analysis role comes into play. Is I had a user that complained that their system's being weird, and that's usually or not working. So you usually have those extremely detailed explanations as to what's going on. It's acting weird. You go in there, you find this install.exe is running in the background. So you reboot the machine in safe mode. You take install.exe off the machine. You keep a copy for yourself, and you go and do these analysis steps. And then you extract information like this, and then you load it into an incident response tool or something like that, and you go to every single other system in your company and try and look for any files on disk that have those strings in them. And then you may find the 5 or 6 other machines where the user wasn't complaining. And that's just because the malware wasn't interfering with with the normal operation of the system. So I'm going to stop the lecture there for today, but we will pick up exactly in that location with like the last slide in my deck plus what I put in the next deck, the next lecture.
What kind of incident response tool would you throw that string into to search through?
Yeah, so there's a lot of different incident response tools out there to do that. So, the question was, where would I put that tool? What incident response tool would I put that tool in? There's a number of ones out there. Let me see, like what I can find on the internet here. I think this one is a good example of one, maybe. Whoops. Oh, it's down there at the bottom, actually. Now I brought it up to the top. So you might be able to use a tool like this. This is an open source incident response tool. It's called Google Rapid Response. So it's an open source project, so you get to see the source code and all the information and all that stuff about it that can help you actually understand what you need to do on a system in order to look for strings like that. So this is a very good learning tool as well. Should recommend looking into it.